Hello and welcome back to the course on machine learning. Today we're talking about Bayes' theorem. Now our main goal for this section is the naive Bayes classifiers, but at the same time we can't proceed to them without talking about Bayes' theorem. That's why we're going to have this lovely tutorial devoted specifically to this topic. So let's kick it off and get straight into it. Today we're talking about spanners. I know it's a bit weird why we're talking about spanners. We're supposed to be talking about Bayes' theorem, but I'm going to be illustrating the Bayes' theorem on an example, and we're going to be using spanners just because it's one of the things that I found on the internet, one of the first pictures that came to mind, and also that way you'll always remember whenever somebody says Bayes' theorem, you'll remember spanner and you'll remember what we talked about today. So it's a good way to anchor this into your memory. All right, so let's say we're at a factory. We're doing some analytics for a factory, and there's two machines, and one machine produces spanners and the other machine produces spanners. Now the machines work at different rates and they have somewhat different characteristics, but overall they're producing the same spanners. The additional information here is that the spanners are actually marked or tagged, so we know which machine they came from. So the top ones came from machine 1, the bottom ones came from machine 2. And then at the end of the day, we've got like a whole pile of these spanners, and the workers go through them, and their goal is to pick out the defective spanners. So here we can see that there's a couple of defective spanners hiding among the pile. Now, the question that we're going to be asking today is, what's the probability? What's the probability of machine 2 producing a defective spanner? So if you take just a random spanner produced by machine 2, so as it comes out of from the conveyor belt, you pick it up, what is the probability that that spanner is defective? And the way we'll get to that probability is through some information that will already be given to us at the start. So we'll have a look at that information in a second, but the rule or the mathematical concept that we'll be using to get to that probability is called the Bayes theorem. Here's a mathematical representation of it. I know it is a bit complicated right now. It seems like, what are all these signs? Like, we know that P is probably probability, but then B, A, and the vertical line, what are all of them doing here? What is this relationship telling us? Well, don't worry about it for now. We will walk through it very slowly, step by step, and you'll get to know the Bayes theorem very intimately. All right, so let's get started. What is the information that is provided to us at the very start? Well, we know that machine 1 produces 30 wrenches per hour and machine 2 20 wrenches per hour. By the way, wrenches and spanners, I found out just now that they're actually the same thing. A spanner is outside of North America, a wrench is inside of North America. So there you go, you learned an extra additional thing today. If you didn't know that, I learned an extra additional thing. So we're just going to call them wrenches from now. Machine 1 produces 30 wrenches, machine 2 produces 20 wrenches per hour. Okay, great. Also, out of all of the produced parts, we can see that 1% are defective. So after checking the parts at the end of the day, thousands and thousands of wrenches, we can see that 1% of them are defective. Okay, so we know that. Then we also know that out of all of the defective parts, we can see that 50% came from machine 1 and 50% came from machine 2. So here you can see that if you take all the defective parts, so only the defective parts, and you calculate how many of them came from machine 1 and how many of them came from machine 2, you'll see that half and half, that half of them are from machine 1 and half of them from machine 2. All right, so this is just the defective parts. And the question is, what is the probability that a part produced by machine 2 is defective? So that's the same question which we discussed already. What is the probability that if I come up to machine 2 and take the part that just popped out of machine 2, what is the probability that that part is going to be defective? So how do we put all of that information together to get the answer to this question? That's what Bayes' theorem answers or helps us do. So let's have a look at how we can rewrite this information in more mathematical terms. So the first line, what does it tell us? It tells us that machine 1 produces 30 wrenches per hour, machine 2 20 wrenches per hour. So in total, out of all the wrenches produced, there's 50 wrenches produced per hour. And also that means that the probability of any given wrench that you pick up from the pile, just any, whether it's defective or non-defective, if you pick up a wrench from the final pile, the probability that it'll come from machine 1 is 30 divided by 50. Right, so if we're producing 30 from machine 1 and 50 overall per hour, that means the likelihood of any given wrench to be from machine 1 is exactly 30 divided by 50, or 0.6, or 60%. Similarly, the likelihood of that wrench being from machine 2 is 20 over 50, or 40%. All right, great. So we're going to write those down and keep them there for now. Now let's see what we can get out of the second line. So we can see that out of all the produced parts, we can see that 1% are defective. Well, it's very simple to rewrite this in mathematical terms. We can just say probability of a part being defective equals 1%. So even though that was a simple transition, actually these sentences are saying a bit different things. So the one on the left says we can see that 1% are defective. So that means that we counted the number of defective parts and we divided by the total amount. And that means that 1% defective. On the right, we're saying the probability of a single part to be defective is 1%. So that means if I pick up a random part from the pile, the likelihood of it being defective is 1%, right? So that is what we're saying here, and it's a very simple thing to write in mathematical terms. There it is, P defective, or that there's a defect, equals 1%. All right, and now we're moving on to part 3. Out of all of the defective parts, we can see that 50% came from machine 1 and 50% came from machine 2. So how do we write that in mathematical terms? And this is the interesting part. So let's start with the machine 1 part. 50% came from machine 1, meaning that if we take only the defective parts, so if it's given that we're only looking at the defective parts, then the likelihood that any part that we pick out, that part came from machine 1 is 50%. And the way to write in mathematical terms is this way. P of machine 1 vertical line defect equals 50%. So the right part over here, the vertical line in mathematical terms means given. So here you can see P of machine 1 means the likelihood or probability of a part coming from machine 1. Here it's the same thing, but given some condition. So this is the likelihood of a part coming from machine 1 given the condition that that part is defective. So you know a priori that that part is defective because you're picking it out of the defective pile. So what is the probability of that part coming from machine 1? Well, it's 50%. And that is the mathematical transcription of this sentence. We can see that 50% came from machine 1, 50% of defective parts. Okay, so now let's do the same thing for the machine 2. It's going to look exactly the same, but here's going to be machine 2. So probability of a part, the part that we just picked up, the probability that it originally was created by machine 2 is 50%, given that we're only picking out from the defective pile, right? Because if we're picking out of all of them, it's actually 40%, it's 0.4. But if we're picking it out only from the defective file, it's 50%. So you can already tell from here, from these two expressions or 4 expressions, that the likelihood of a part coming from machine 2 is 40%, meaning that it produces less. It produces less wrenches. Whereas the likelihood of a defective part coming from machine 2 is 50%. So that if you take any part or any wrench, you pick it out from the defective pile, the likelihood that it was originally produced by machine 2 is 50%. So you can tell right away that machine 2 seems to be producing disproportionately more defective parts than machine 1, right? So it's only producing 40% of the output, but it's accounting for 50% of the defective parts. And the question that we want to ask is actually a bit different, right? So the question we want to ask is, what is the probability that a part produced by machine 2 is defective? So here it's kind of reverse. Here we're saying we're taking a part from machine 2, right? We're only looking at parts that are produced by machine 2. What is the probability of a random part taken out of machine 2 to be defective? How do we write that in mathematical terms? It's written this way. So probability of a defective part given that it came from machine 2. If you look at just the probability of a part being defective, it's 1%. But here we're given a condition that it's machine 2. So the way to think of it, you can either think of it as parts are coming out of machine 2 and you just pick up a random one. What's the probability of it being defective, right? Or you can think of it in terms of quantities. The correct term here is frequentist interpretation. So you can think of it in terms of the frequentist interpretation, and that means instead of just picking up one part and thinking about what is the likelihood of it being defective, if we know that it came from machine 2, think of it as there's a pile of wrenches that only came from machine 2. So you have a pile of 1,000 wrenches that came from machine 2. What is the number of wrenches that are going to be defective, right? So what is the portion of wrenches that are going to be defective? So those are two different ways of thinking about probabilities or the Bayes theorem, but they're pretty much the same thing. They're exactly the same thing. It just different ways of thinking about it. So it's either what's the probability of this one part that just came out of machine 2 being defective, or what is the portion of all of these parts that came out of machine 2, what is the portion of them that's going to be defective? So that's the question that we want to answer given all this information. All right, so let's start solving this problem, and we'll illustrate how the Bayes theorem will help us convert this information to this information. All right, so first of all, we won't need the probability for machine 1 and the probability for machine 1 given defective. So we're going to get rid of that out of our information just to clean things up. Okay, and now let's just move everything, slide everything over to make some space. And now let's write down the Bayes theorem, which we had a brief look at before. The Bayes theorem for this particular problem will look as follows. So the probability of a defective part, given that it came from machine 2, so a probability of a part being defective, given that that wrench came from machine 2, equals, and here we go, this is the fun part. So you will take the probability, we'll start from right to left. We'll take the probability of a part being defective overall. We will need to multiply that by the probability that a part came from machine 2, given that it was defective. And we will need to divide that by the probability of the part coming from machine 2. All right, so for now, this might seem a bit better already than we saw previously. At least now we can read these terms, right? And we know how we got them here. So we actually discussed each one of these terms, and they're pretty straightforward, even though the mathematical representation might look a bit scary. At the same time, they're pretty straightforward terms. We know what we're talking about. At the same time, we don't really understand where this formula came from, and more importantly, on intuitive level, it doesn't really make sense at this stage. But it's okay. Let's, for now, plug in the numbers, and then we'll proceed to the intuitive part of this formula. So if we plug in the numbers, what we'll get is 0.5. So we'll just take numbers from the top, or if we start from right to left again, the probability of a part being defective overall is 1%. Multiplied by probability of a part coming from machine 2, given that we're only looking at defective parts, or given that that part is known to be defective, it's 50%, so there it is. And we're dividing that by the probability of the part coming from machine 2 overall, and that is 40%. So there you go. So if we plug that in, we get 0.0125. So 1.25 percentages, or 1.25%. is the probability that machine 2 will spit out a defective part, right? So if you come up to machine 2 and you pick up a part, then the probability of that part being defective is 1.25%. Or the frequentist interpretation is, if machine 2 produced 1,000 parts, then according to Bayes' theorem, 12.5 of them will be defective. So you can't really say 12.5 wrenches will be defective. So let's say it produced 10,000 parts, then the Bayes theorem tells us that 125 of those wrenches are going to be defective. So as you can see, we converted all this information that we knew about the process and about the results of the process into exactly what we want. Now let's move on to the intuition, the fun stuff, right? So there's 1.25%. So let's move this to the top. That's our Bayes theorem. And let's look at an example, and you'll see that it's actually very, very intuitive what we just did. It all makes total sense. So let's look at an example. Let's say we produced 1,000 wrenches all total. So in total, we have 1,000 wrenches after the two machines were working for some time. So we know that 400 of them came from machine 2, right? So we know that machine 2 produces, how many wrenches per hour does it produce? Produces 20 wrenches per hour, and machine 1 produces 30 wrenches per hour, as per our information from the very start. And that means that out of the 1,000 wrenches, 40% would have been produced by machine 2. That means 400 came from machine 2. Okay, so that makes total sense. Then we also know that 1% have a defect. We actually see this. The workers who look at the wrenches at the end of the day, this was also given to us, they see that 1% have a defect, and that means out of 1,000, 1% is 10. So 10 wrenches have a defect. Okay, great. And so what's the next step? Next step is that we know that 50% of those 10 came from machine 2. So we know that exactly 5 of those defective wrenches came from machine 2. That was also given to us because those defective wrenches actually have labels on them, and we can tell by the labels that 5 of them came from machine 2. All right, so the question is, what is the percent defective parts from machine 2? Well, it's very easy now, right? Because we know that how many defective actually came from machine 2, 5. And we know how many wrenches came from machine 2, 400, right? So all we have to do is divide 5 by 400 and we'll get 1.25, right? So we get the same answer. Not only do we get the same answer, we actually did exactly the same process. If you think through what we did here, we performed exactly the same process. We had 1,000 wrenches, right? And then we turned that into 400. So we multiplied 1,000 wrenches by 40%, which is the probability of a part coming from machine 2. So this is our denominator, right? So instead of probability of machine 2, what we just did, this 400 is P of machine 2 times 1,000, right? So we have P of machine 2 times 1,000 in the denominator instead of just P of machine 2 in what we're doing here, right? And then 1% have a defect. And that means 10. So where did this 10 come from? That's 1% times 1,000. So instead of P defect at the top, we actually have P defect times 1,000 right now. So just visualize that for a second. So instead of P machine 2, we have P machine 2 times 1,000, P defect times 1,000. And then this 50%, the probability of them 50% came from machine 2, right? Equals 5. This line is actually us performing this operation here. We're saying the probability of card coming from machine 2, given that it's defective, is 50%. So basically, to get to this, what we did is we took this part, so we took 50%, we multiplied it by the 10, which is actually, so we took 50%, multiplied it by 1% times 1,000. So here we've got extra times 1,000. And here we've got P machine 2. What we did is we actually put in P machine 2 times 1,000. So I just added an extra part over here times 1,000 and part over here times 1,000. And then we still divided that final result, that 5 that we got, by the 400 that we got. So the logical steps that we took are exactly the same as the Bayes theorem. The only difference is that we looked at a specific example of 1,000 wrenches. So as you can see, the Bayes theorem is a very intuitive theorem. So we're not even going to go into the mathematics of how it's derived. This is about us understanding it intuitively. So as long as you remember the mathematical representation of the Bayes theorem, it actually makes total sense what it is helping us calculate and in the steps that it is implying for us to take to calculate the final result. So there we go. Hopefully that all makes sense. And we only have one final question left. We only have one obvious question here. So the question is, why do we have to go through all of this complexity? Why do we have to go through all this complexity? Why can't we just count the number of defective wrenches from machine 2 and then count the number of total wrenches that came from machine 2 and divide one by the other and get that same result? Why can't we just do that? Why don't we have that input of the total number of wrenches that came from machine 2 right away? So that's the question. If the items are labeled, why couldn't we just count the number of defective wrenches that came from machine 2 and divide by the total number that came from machine 2? So if you think about it, that's exactly what we are doing. So we're dividing the total number of, so this is the total number of wrenches that came from machine 2. At the top, if you multiply it by the 1,000, at the top we've got the number of machine 2, so defective, the probability of a part coming from machine 2 if it's given that it's defective times the probability of it being defective. So at the top, as you remember, we got that 5. So the top is actually the number of defective parts that came from machine 2. At the end of the day, we're actually doing that exact thing. The question is, why couldn't we do it right away? Why couldn't the workers just go and count the number of defective parts that came from machine 2 and divide it by the number of parts the overall number of parts that came from machine 2? Why not save some time? Well, the answer to that question can be multifold. First of all, it might be very time consuming. Like in this example, it might be time consuming to calculate the number of wrenches that just came from machine 2. For instance, we might know this might be like a standard metric that the factory measures how many wrenches produced overall, right? So we know that number 1,000 or maybe 100,000. But to count them from machine 2, it might take them some time to sit and count through those wrenches, and therefore it's just faster to use Bayes theorem. The other thing here is that sometimes you might not have access to that information. Sometimes the problem might be such that you just cannot perform that, and you have some inputs like we had in this case, and that's it. And it's not as simple as in this example, and therefore you just don't have access to that information. So there are numerous reasons why you could be in a situation where you can't just go through the straightforward, easy, obvious way, and you need to use Bayes theorem. So therefore, it's a useful thing to have in your data science arsenal. And moreover, now that we know Bayes' theorem, we can proceed to the naive Bayes classifiers. And to finish off today's tutorial, I've got a quick exercise for you. Perform the same calculation or similar calculations for this value that we want to calculate. What is the probability of a part being defective given that it came from machine 1? So there you go. It's a handy quick exercise just to solidify this knowledge, and I look forward to seeing you in the next tutorial. Until then, enjoy machine learning.